Hello, testing my mic here.
Once everything's perfectly organized, I'll start working on my thesis.
This comprehensive
Alright, guess what? Power went out again. So here I am again, resuming the course. I'm not gonna give much of an introduction now, let's just get started. So we were troubleshooting this error that we got. Let's continue to do that now.
Welcome back. In the last video, we covered how to go from raw logits, which is the output of the model, the raw output of the model for a multi-class Pytorch model. Then we turned our logits into prediction probabilities using torch.softmax. Value occurs in classes. We would take that in labels are so torch.manual seeds to transform to the CPU. This is we're going to go. Otherwise, we'll loop through data. Points of pain here. Blog. Just take
all of that.
Beautiful. There's a thing of 10 blog turn us and see what to these. What's for a little hint of maybe we have to. So I'll just that we know float or int or something like that. It generally hints at one of your data types being wrong. And so the error is actually right back up here where we created our tensor data. So we turned our labels here into floats, which generally is okay in Pytorch. However, this one should be of type torch.long tensor, which we haven't seen before. But if we go into torch long tensor, let's have a look. Torch.tensor. Do we have long tensor? Here we go. 64-bit integer signed. So why do we need torch.long tensor? And again, this took me a while to find. So I want to express this, that in your own code, you probably will butt your head up against some issues and errors that do take you a while to find. And data types is one of the main ones. But if we look in the documentation for cross-entropy loss, the way I kind of found this out was this little hint here. The performance of the criterion is generally better when the target contains class indices, as this allows for optimized computation. But I read this, and it says target contains class indices. And I'm like, ours are indices already, but maybe they should be integers and not floats. But then, if you actually just look at the sample code, you would find that they use dtype equals torch.long. Now, that's the thing with a lot of code around the internet, is that sometimes the answer you're looking for is a little bit buried. But if in doubt, run the code and butt your head up against the wall for a bit and keep going. So let's just rerun all of this and see, do we have an error here? Let's train our first multi-class classification model together. No errors, fingers crossed. Oh, what did we get wrong here? Okay, so we've got different size. We're slowly working through all of the errors in deep learning here. Value error, input match size 200 to match target size 200. So this is telling me maybe our
expected floating point type for target class probabilities got long. And that. Run this again.
Test data, which is of size 200, is getting mixed up with our training data, which is of size 800. So we've got test loss, the test logits.
So we can't have a long first one. In that case, let's convert this into float whenever we calculate the loss. Oh, okay, it should be torch.float. See, we have run into the same error again, element 0 of tensors.
Model 4, what's the size? Let's print out print test logits.shape and yblob test. So troubleshoot yblob test equals, oh, there we go. Did you catch that before? Maybe you did, maybe you didn't, but I think we should be right here. Now, if we just comment out this line. So we've had a data type issue and we've had a shape issue. Two of the main machine learning. Oh, and again, we've had some issues. Yblob test, what's going on here? I thought we just changed the shape. Oh no, we have to go up and reassign it again because, now this is definitely yblob, yes. Let's rerun all of this, reassign our data. We are running into every single error here, but I'm glad we're doing this because otherwise you might not see how to troubleshoot these type of things. So the size of a tensor match the size. Oh, we're getting the issue here. Test preds. Oh my goodness, we have written so much code here.
Oh, okay.
Test pred. So instead of y pred, this should be test preds. Fingers crossed. Are we training our first model yet or what? There we go.
Alright, okay, wait. Element 0. Quality test. Dynamic calling. Element 0 of tensors does not require grad and does not have a grad function. Yeah, it is in training mode. Let's just create the model again and run it. I thought that might fix it. Apparently not. Yeah. Come on, we can pull through this. Element 0 of tensors does not require grad and does not have a grad function. I have a feeling this is to do something with us converting the type to float.
Go. So the size. Now this is definitely y blob. Yes. Let's rerun all of this, reassign our data.
All right. You know what? Let's just go to the code section. Not the code section. The code section. Data. Not data. Express. Going modular. No, not that. Model 4. Requires grad. Then we create the. Okay, let's check everything. Model created correctly. They have not used relu layers yet, but in the video they have. So let's just fix that. Epochs comparing train, blob train, test, blob test, train. Yep, we get the logics first. Cool. Then we get the. Yeah, we can do it this way too. Should be fine. Then the loss. Another day of me being a programmer. Alright, so I guess that should fix it then. Ah, finally.
We are running into every single spreads. Going to, in fact, friends, there we go. Okay, and we're printing out some stuff. I don't really want to print out that stuff, and I want to see the loss go down. So I'm going to, so friends, I hope you know that we've just been through some of the most fundamental troubleshooting steps. And you might say, oh, Daniel, that's a cop out because you're just coding wrong. And in fact, I code wrong all the time. But we've now worked out how to troubleshoot them, shape errors and data type errors. Oh, look at this. After all of that, thank goodness, our loss and accuracy go in the directions that we want them to go. So,
What happened here?
oh, look at this. I code wrong all the time. But we've now worked out how to troubleshoot them, shape errors and data type errors. Oh, look at
Our loss isn't going down. Something's up. Well, let's just try it a bit more. Nope, nothing's happening. Oh, did we reassign the model? If we reassign the model, then we need to, because the address would change, right, where it lives. Maybe that's the reason. Yep, that was the reason.
this.
Alright.
After all of that, thank goodness, our loss and accuracy
Yep,
go in the
thank
directions that we want them to go.
indeed.
So our loss goes down and our accuracy goes up. Beautiful. So it looks like that our model is working on a multi-class classification data set. So how do we check that? Well, we're going to evaluate it in the next step by visualize, visualize, visualize. So you might want to give that a shot. See if you can use our plot decision boundary function. We'll use our model to separate the data here. So it's going to be much the same as what we did for binary classification, but this time we're using a different model and a different data set. I'll see you there. Welcome back. In the last video, we went through some of the steps that we've been through before in terms of training and testing our model, but we also butted our heads up against two of the most common issues in machine learning and deep learning in general, and that is data type issues and shape issues. But luckily, we were able to resolve them. And trust me, you're going to run across many of them in your own deep learning and machine learning endeavors. So I'm glad that we got to have a look at them and sort of I could show you what I do to troubleshoot them. But in reality, it's a lot of experimentation. Run the code, see what errors come out, Google the errors, read the documentation, try again. But with that being said, it looks like that our model, our multi-class classification model has learned something. The loss is going down, the accuracy is going up. But we can further evaluate this by making and evaluating predictions with a Pytorch multi-class model. So how do we make predictions? We've seen this step before, but let's reiterate. Make predictions. We're going to set our model to what mode? Eval mode. And then we're going to turn on what context manager? Inference mode. Because we want to make inference. We want to make predictions. Now, what do we make predictions on? Or what are the predictions? They're going to be logits. Because why? They are the raw outputs of our model. So we'll take model 4, which we just trained, and we'll pass it the test data. Well, it needs to be blob test, by the way. I keep getting that variable mixed up. We just had enough problems with the data, Daniel. We don't need any more. You're completely right. I agree with you. But we're probably going to come across some more problems in the future. Don't you worry about that. So let's view the first 10 predictions. Why logits? What do they look like? All right, just numbers on the page. They're raw logits. Now, how do we go from logits to prediction probabilities? How do we do that? With a multi-class model, we go y_pred_probs equals torch.softmax on the y logits. And we want to do it across the first dimension. And what do we have when we go pred_probs? Let's go up to the first 10. Are we apples to apples yet? What does our y blob test look like?
We have a y logits. Time to get probabilities, prediction probabilities. Hey, we have another viewer. Oh, never mind, I guess. Talk too soon. Okay. Anyway, prediction probabilities. We're gonna do torch dot. So we want to use, what do we need to use here? Yeah, torch.softmax.
We're not apples to apples yet, but are we apples to apples yet? What does our Y blob test look like? We're not apples to apples yet, but we're close. So these are prediction probabilities. You'll notice that we get some fairly different values here. And remember, the one closest to 1 here, the value closest to 1, which looks like it's this, the index of the maximum value is going to be our model's predicted class.
Yeah.
So this index is index 1, and does it correlate here? Yes, 1, beautiful. Then we have index 3, which is the maximum value here. 3, beautiful. And then we have, what do we have here? Index 2, yes, okay, wonderful. But let's not step through that. We're programmers. We can do this with code. So now let's go from pred probs to pred labels. So y preds equals, how do we do that? Well, we can do torch.argmax on the y pred probs, and then we can pass dim equals 1. We could also do it this way, y pred probs called .argmax. There's no real difference between these two, but we're just going to do it this way, called torch.argmax, y preds. Let's view the first 10. Are we now comparing apples to apples when we go y blob test? Yes, we are. Have a go at that. Look, 1, 3, 2, 1, 0, 3, 1, 3, 2, 1, 0, 3. Beautiful. Now we
Not beautiful. What is happening here?
could line these argmax to do it this way. Also, how do we do that? Well, we can do torch.argmax on the y pred probs, and then we can pass dim equals 1. We could also do it logits. Now, how do we go from logits to prediction probabilities? How do we do that? With a multi-class model, we go y pred probs equals torch.softmax on the y logits. And we want to do it across the first dimension. And what do we have when we go pred probs? Let's go up to the first 10. Are we apples to apples yet? What does our y blob test look like? We're not apples to apples yet, but we're close. So these are prediction probabilities. You'll notice that we get some fairly different values here. And remember, the one closest to 1 here, the value closest to 1, which looks like it's this, the index of the maximum value is going to be our model's predicted class. So this index is index 1, and does it correlate here? Yes, 1, beautiful. Then we have index 3, which is the maximum value here. 3. Beautiful. And then we have, what do we have here? Index 2, yeah. So 1 equals 1. We could also do it this way. Y preds, let's go at that. Look, 1, 3, 2, 1, 0, 3, 1, 3, 2.
Alright, what should we do here exactly? Why do you have a gradient function? You know what? Let's just create the model again, put it into the loss function, train the model again, this time from the logits. Okay, do this, don't do this.
But probs. Okay, well, we have index maximum probability. Class model. How do we go? Let's view the first 10 predictions. Y logits. What do they look like? All right. Just numbers on the page. They're all logits. Now, how do we go from logits to prediction probabilities? How do we do that? With a multi-class model, we go y pred probs equals torch.softmax on the y logits. And we want to do it across the first dimension. And
Yes, I agreed.
what do we have when we go pred probs? Let's go up to the first 10.
We made a typo there. Yep,
Are we
that
apples to
resolved
apples yet?
that.
What does our Y blob test look like?
It's the silly
We're
errors
not apples to apples yet, but we're close. So these are prediction probabilities. You'll notice that we get some fairly different values here. And remember, the one closest to 1 here, the value closest to 1, which looks like it's this, the index of the maximum value is going to be our model's predicted class. So this index is index 1. And does it correlate here? Yes, 1. Beautiful. Then we have index 3, which is the maximum value here. 3. Beautiful. And then we have, what do we have here? Index 2. Yes, okay, wonderful. But let's not step through that. We're programmers. We can do this with code. So now let's go from compare 0 to something. We're actually glad that we did that because seriously, what shown is I kind of know when ingredients work from ahead of time, despite what you saw in the last video with all of that troubleshooting. But I'm actually glad that we did that because seriously, shape issues and data type issues, you're going to come across a lot of them. They're two of the main issues I troubleshoot, aside from device issues. So let's go X blob train and Y blob train. And we're going to do another plot here. We're going to get subplot 1, 2, 2. And we're going to do this for the test data. Test, and then plot decision boundary. Plot decision boundary with model 4 on X blob test and Y blob test as well. Let's see this. Did we train a multi-class? Oh my goodness, yes we did! Our code
Wait, I need to see that first on my system, but I guess apparently not. Anyhow, plot decision boundary. Pass in the model and pass in our training data, our features, and our, let's pass in our labels. Similarly, create another, you know what, let's just copy this, create another subplot, this time for the testing data sets, test data sets rather, not testing data sets. And then do that, and then just run that. There we go.
faster than I can speak. Look at that beautiful looking plot. We've separated our data almost as best as what we could. Like there's some here that are quite inconspicuous. And now, what's the thing about these lines? Would this model have worked? I posed the question a fair few videos ago, whenever we created our multi-class model, that could we separate this data without nonlinear functions? So how about we just test that? Since we've got the code ready, let's go back up. We've got non.
We're just gonna comment this out. I'll test it first. Created that. Creating the loss function again. Oh gosh, I don't know if that sound is being heard on the stream. Plane is just going, you know, about the roof right now. Okay. That and
linear functions here. We've got ReLU here. So I'm just going to recreate our model there. So I just took ReLU out. That's all I did. Commented it out. This code will still all work. Out of straighter here. Did we get different metrics? I'll leave that for you to compare. Maybe these will be a little bit different. I don't think they're too far different. But that is because our data is linearly separable. So we can draw straight lines only to separate our data. However, a lot of the data that you deal with in practice will require linear and nonlinear. Hence why we spent a lot of time on that. Like the circle data that we covered before. And let's look up an image of a pizza. If you're building a food vision model to take photos of food and separate different classes of food, could you do this with just straight lines? Well, you might be able to, but I personally don't think that I could build a model to do such a thing. And in fact, Pytorch makes it so easy to add nonlinearities to our model, we might as well have them in so that our model can use it if it needs it, and if it doesn't need it, well, hey, it's going to build a pretty good modle, as we saw before, if we included the nonlinearities in our model. So we can uncomment these, and our model is still going to perform quite well. That is the beauty of neural networks, is that they decide the numbers that should represent our data the best. And so, with that being said, we've evaluated our model, we trained our multi-class classification model, we put everything together, we've gone from binary classification to multi-class classification. I think there's just one more thing that we should cover, and that is, let's go here, section number 9, a few more classification metrics. So, as I said before, evaluating a model, let's just put it here, to evaluate our model, our classification models, that is. Evaluating a model is just as important as training a model. So I'll see you in the next video. Let's cover a few more classification metrics. Welcome back. In the last video, we evaluated our multi-class classification model visually. And we saw that it did pretty darn well, because our data turned out to be linearly separable, so our model, even without nonlinear functions, could separate the data here. However, as I said before, most of the data that you deal with will require some form of linear and nonlinear function. So just keep that in mind, and the beauty of Pytorch is that it allows us to create models with linear and nonlinear functions quite flexibly. So let's write down here, if we wanted to further evaluate our classification models, we've seen accuracy. So accuracy is one of the main methods of evaluating classification models. So this is like saying, out of 100 samples, how many does our model get right? And so we've seen our model right now is at testing accuracy of nearly 100%, so it's nearly perfect. But of course, there were a few tough samples, which I mean, a little bit hard. Some of them are even within the other samples, so you can forgive it a little bit here for not being exactly perfect. What are some other metrics here? Well, we've also got precision, and we've also got recall. Both of these will be pretty important when you have classes with different amounts of values in them, so precision and recall. Accuracy is pretty good to use when you have balanced classes. So this is just text on a page for now. F1 score, which combines precision and recall. There's also a confusion matrix, and there's also a classification report. So I'm going to show you a few code examples of where you can access
I know what accuracy is. I have heard what precision is, but I don't know what the other metrics are. So let's
these,
take
and I'm
a
going to
look
leave
at
it to you
that.
as extra curriculum to try each one of these out. So let's go into the keynote. And by the way, you should pat yourself on the back here because we've just gone through all of the Pytorch workflow for a classification problem. Not only just binary classification, we've done multi-class classification as well. So let's not stop there though. Remember, building a model, evaluating a model is just as important as building a model. So we've been through nonlinearity. We've seen how we could replicate nonlinear functions. We've talked about the Machine Learning Explorer's motto, visualize, visualize, visualize. Machine Learning Practitioner's motto is experiment, experiment, experiment. I think I called that Machine Learning or Data Scientist motto. Same thing, you know? And steps in modeling with Pytorch, we've seen this in practice, so we don't need to look at these slides. I mean, they'll be available on the GitHub if you want them, but here we are. Some common classification evaluation methods. So we have accuracy. There's the formal formula if you want, but there's also code, which is what we've been focusing on. So we wrote our own accuracy function, which replicates this. By the way, TP stands for not toilet paper, it stands for true positive. TN is true negative, false positive, FP, false negative, FN. And so the code, we can do torch metrics. Oh, what's that? But when should you use it? The default metric for classification problems. Note, it is not the best for imbalanced classes. So if you had, for example, 1,000 samples of one class, so number one, label number one, but you had only 10 samples of class 0. So accuracy might not be the best to use for then. TN is true negative, false non. So we wrote our classification evaluation methods. So we have accuracy. There's the formal formula if you want, but there's also code, which is what we've been focusing on. So we wrote our own accuracy function, which replicates this. By the way, TP stands for not toilet paper, it stands for true positive. TN is true negative, false positive, FP, false negative, FN. And so the code, we can P stands for not toilet paper, it stands for true positive. TN is true negative, false positive, FP, false negative, FN. And so the code, we can do torch metrics. Oh, what's that? But when should you use it? The default metric for classification problems. Note, it is not the best for imbalanced classes. So if you had, for example, 1,000 samples of one class, so number one, label number one, but you had only 10 samples of class 0. So accuracy might not be the best to use for then. For imbalanced data sets, you might want to look into precision and recall. So there's a great article called, I think it's Beyond Accuracy, Precision and Recall, which gives a fantastic overview of, there we go, this is what I'd recommend. There we go, by Will Coestrin. So I'd highly recommend this article as some extra curriculum here. See this article for when to use precision recall. We'll go there. Now if we look back, there is the formal formula for precision, true positive over true positive plus false positive. So higher precision leads to less false positives. So if false positives are not ideal,
higher precision leads to less false positives.
You probably want to increase precision. And if false negatives are not ideal, you want to increase your recall metric. However, you should be aware that there is such thing as a precision recall trade-off, and you're going to find this in your experimentation. Precision recall trade-off. So that means that generally, if you increase precision, you lower recall, and inversely, if you increase precision, you lower recall. So check out that just to be aware of that. But again, you're going to learn this through practice of evaluating your models. If you'd like some code to do precision and recall, you've got torchmetrics.precision or torchmetrics.recall, as well as scikit-learn. So scikit-learn has implementations for many different classification metrics. Torchmetrics is a Pytorch-like library. And then we have F1 score, which combines precision and recall. So it's a good combination if you want something in between these two. And then finally, there's a confusion matrix. I haven't listed here a classification report, but I've listed it up here. And we can see a classification report in scikit-learn. Classification report. Classification report kind of just puts together all of the metrics that we've talked about. And we can go there. But I've been talking a lot about torch metrics. So let's look up torch metrics accuracy. Torch metrics. So this is a library. I don't think it comes with Google Colab at the moment, but you can import torch metrics and you can initialize a metric. So we've built our own accuracy function, but the beauty of using torch metrics is that it uses Pytorch-like code. So we've got metric, preds, and target, and then we can find out what the value of the accuracy is. And if you wanted to implement your own metrics, you could subclass the metric class here, but let's just practice this. So let's check to see if, I'm going to grab this and copy this in here. If you want access to a lot of Pytorch metrics, see torch metrics. So can we import torch metrics? Maybe it's already in Google Colab. No, not here, but that's all right. We'll go pip install torch metrics. So Google Colab has access to torch metrics, and that's going to download from torch metrics. It shouldn't take too long. It's quite a small package, beautiful. And now we're going to go from torch metrics, import accuracy. Wonderful. And let's see how we can use this. So set up metric. So we're going to go torch metric underscore accuracy. We can call it whatever we want really, but we need accuracy here. We're just going to set up the class, and then we're going to calculate the accuracy of our multi-class model by calling torch metric accuracy, and we're going to pass it y_preds and y_blob.
The download is taking a bit of time for me. I don't know why. I have a good internet connection, so anyhow, let's just try to follow along with the tutorial.
Test. Let's see what happens here. Oh, what did we get wrong?
Don't we need to pass in the test first?
And we're going to pass it y_preds and y_blob test. Let's see what happens here. Oh, what did we get wrong? Runtime error. Expected all tensors to be on the same device, but found at least 2 devices. Oh, of course.
Maybe it's just for scikit-learn. That's what Daniel.
Now, remember how I said torch metrics implements Pytorch-like code? Well, let's check what device this is on. Oh, it's on the CPU. So something to be aware of that if you use torch metrics, you have to make sure your metrics are on the same device by using device agnostic code as your data. So if we run this, what do we get? Beautiful. We get an accuracy of 99.5%, which is in line with the accuracy function that we coded ourselves. So if you'd like a lot of pre-built metrics functions, be sure to see either scikit-learn for any of these or torch metrics for any Pytorch-like metrics, but just be aware, if you use the Pytorch version, they have to be on the same device. And if you'd like to install it, what do we have? Where's the metrics? Module metrics. Do we have classification? There we go. So look how many different types of classification metrics there are from Torch metrics. So I'll leave that for you to explore. The resources for this will be here. This is an extracurriculum article for when to use precision recall, and another extracurriculum would be to go through the Torch metrics module for 10 minutes and have a look at the different metrics for classification. So with that being said, I think we've covered a fair bit. But I think it's also time for you to practice what you've learned. So let's cover some exercises in the next video. I'll see you there. Welcome back. In the last video, we looked at a few more classification metrics, a little bit of a high-level overview for some more ways to evaluate your classification models. And I linked some extra curriculum here that you might want to look into as well, but we have covered a whole bunch of code together. But now it's time for you to practice some of this stuff on your own. And so I have some exercises prepared. And where do you go for the exercises? Well, remember, on the learnpytorch.io book, for each one of these chapters, there's a section. Now, just have a look at how much we've covered. If I scroll, just keep scrolling. Look at that. We've covered all of that in this module. That's a fair bit of stuff. But down the bottom of each one is an exercises section. So all exercises are focusing on practicing the code in the sections above, all of these sections here. We've got number 1, 2, 3, 4, 5, 6, 7. Yeah, 7 exercises, nice, writing plenty of code. And then, of course, extra curriculum. So these are some challenges that I've mentioned throughout the entire section 02. But I'm going to link this in here, exercises. But of course, you can just find it on the learnpytorch.io book. So if we come in here and we just create another heading, exercises and extra curriculum. And then we just write in here, see exercises and extra curriculum here. And so if you'd like a template of the exercise code, you can go to the Pytorch Deep Learning repo. And then within the extras folder, we have exercises and solutions. You might be able to guess what's in each of these. Exercises, we have O2 Pytorch classification exercises. This is going to be some skeleton code. And then, of course, we have the solutions as well. Now, this is just one form of solutions, but I'm not going to look at those because I would recommend you looking at the exercises first before you go into the solutions. So we have things like import torch, set up device agnostic code, create a data set, turn data into a data frame, and then et cetera, for the things that we've done throughout this section. So give that a go, try it on your own, and if you get stuck, you can refer to the notebook that we've coded together, all of this code here. You can refer to the documentation, of course, and then you can refer to, as a last resort, the solutions notebooks. So give that a shot, and congratulations on finishing section 02, Pytorch classification. Now, if you're still there, you're still with me?
Yep.
Let's move on to the next section. We're going to cover a few more things of deep learning with Pytorch. See you there.
All right. I guess we call it a day for now. We've learned quite a lot today. We finally finished, well, we finished binary classification a while ago, and we've also finished multi-class classification alongside with it. Now, I'm going to end the stream, but before we do that, I want to see whether what happens if we increase this to 5. How does our model react? Now we have orange dots. I guess with this we need to give it let's just enable relu, the relu layer, run this, train the model, train it a bit more. Okay, maybe 1,000 times. It's not increasing beyond 92.5. I mean, let's just view it. There we go. That looks good. You know what happens if we increase the number of layers? So I guess we can't do it. Wait a second, we have 5 yeah, I would have said num class is that. Something we can do though is let's just try increasing the layers and see. And as I said, I'll end the stream. I will, but let's just do this and see what happens. Hidden units, and the relu in between these. Maybe change the yeah, let's also change the hidden units to 32. Right, and go ahead and create our loss functional optimizer, and finally train it. That actually decreased our accuracy. Anyway, let's just do this. Maybe if we had spent some time testing around, we might come to a high accuracy, but it's not bad. I guess part of it is because it's all collide together, like the blue and the orange just collides together and all. But yeah, I guess it's all looking good. And yeah, we've made quite a lot of progress, and I'm really happy with the progress we made. So I'm gonna end this stream now, and as always, I'll see you in the next one. Take care till then.